Greetings to all and welcome to this lecture. We are in module 2, which is two-terminal MOS structure, and lecture number 4, general analysis 1. In this lecture, we are going to formulate a general relationship between the charge, which is channel charge, and the applied gate voltage, which is nothing but VGB. You remember that in previous lectures, we were discussing about two-terminal MOS structure, where this is metal, this layer is oxide, and this is semiconductor. We were applying a voltage between gate and body terminal, which is VGB. And we claimed that by applying a VGB, there is a surface potential come into picture. This surface potential is actually responsible for causing a channel charge. So here we are trying to formulate a closed form equation relating these three quantities, psi s, QC dash, and applied VGB. These are the learning outcomes of this lecture, where you will get the idea how to relate the surface potential, carrier concentration, charge density in MOS structure as a function of applied gate voltage. Let's do a quick recap. In previous lectures, we were discussing about the two-terminal MOS structure, where we said that the application of gate to body voltage causes different condition in MOS capacitor or two-terminal MOS structure. So, based on the applied voltage with respect to flat band voltage, we decide that whether it is in accumulation, depletion, or in inversion. We said that when VGB is exactly equals to flat band voltage, then there is no charge pile up into the semiconductor, and hence the surface potential as well as the charge, the channel charge, is 0 under flat band condition. Now, when the applied voltage is less than flat band voltage, it means you are in accumulation. So, ultimately the surface potential is negative and the channel charge is positive. So, in the accumulation, your channel charge is positive and the surface potential is negative. Now, what will happen if I increase VGB towards the positive side? If I increase VGB towards the positive side, this positive charge present on the metal causes a negative charge into this plate, and hence the surface potential is positive and the channel charge is negative. We have seen two different conditions of VGB values. If VGB is greater than V flat band voltage but equal to phi f, then we are in depletion. But when VGB is so high such that my surface potential is greater than phi f but less than 2 phi f, we are in weak inversion. When surface potential increases to 2 phi f, we are in inversion. We have also seen how my surface charge is related with the body charge or the body doping, which is Na e to the power of psi s minus 2 phi f over phi t. So, when the surface potential exceeds the 2 phi f value, then N surface is exponentially increasing above the substrate doping. Let us get started with a general analysis, a general formulation. We will try to formulate an equation of channel charge and surface potential in such a way that it should satisfy all the conditions. It means whether my MOS structure in accumulation, depletion, or inversion. For that, we will go with our basic fundamental of junction law. What we said earlier, the junction law helps us to relate the doping concentration with the voltage present between that doping concentration. Meaning, if you have two doping concentration regions or two regions of different doping concentration N1 and N2, and there will be a potential developed between that, which is plus, minus and psi, then I can write an equation N1 is equals to N2 exponential of plus psi by phi t, because this positive charge or this positive side of the potential will attract much more electron from N2 to N1, and hence this will become a positive exponential. Keeping in mind that if it is N2, then it will be n1 exponential of minus psi by phi t, because the direction or the polarity of the potential is opposite. So we are applying the same junction law here at the surface. Now in the two terminal MOS structure, this is gate, this is body, and we are applying a gate to body voltage externally. This gate to body voltage is nothing but psi ox plus psi s plus phi ms. You remember the potential balance equation, VGB is equals to phi ms plus psi ox plus psi s, right. Now, so you take it like this: if you are applying a positive voltage in the gate, then this positive charge requires a negative charge into the surface, right. Then there will be a depletion region and there will be an inversion region. Will the depletion region expand, go below to the body? So to understand that, let us take an analogy. Let us consider a MOS structure, a two terminal MOS structure MOS with gate and body terminal, and you are applying a VGB here. This MOS structure is similar as a piece of land. Now if the gate to body voltage is 0, means the land is flat, so nothing special in it. But when you increase the gate to body voltage, it means what will happen? You are making a pit, right, into the land surface, right. Digging a pit means you are removing the soil from here, which is similar as removing the holes from the surface of the semiconductor. So if you apply a positive voltage, then the positive holes will be removed from the surface, and removing the holes from the surface is equivalent to causing a depletion region. So the empty pit is nothing but similar as depletion region. Then if you increase VGB, the height of this pit will go on increases. But can you increase the height of this pit so longer or so deeper? No, because even if you apply so much force to remove the soil, what will happen? After a certain point, the groundwater will leak and come to the surface. That groundwater is nothing but the inversion charge. So this is similar as when you apply the gate voltage, there will be a depletion region, then increasing the gate voltage will increase the depletion region thickness, and this depletion region thickness will get stopped after a certain value. So let me make like this, after a certain value, and then inversion charge will come into picture. These inversion charge are nothing but taken from the body itself, which are minority charge carrier concentration, correct. So there will be a potential drop across this surface which causes this inversion or depletion. That what we called is surface potential. Let us consider that this dimension is x dimension and this dimension is y dimension. So we are going to calculate or formulate the relation in terms of y, not considering surface potential as of now. We are actually formulating the general formula. So what will happen? This is psi y, and hence the electron concentration near the surface, right, is equal to ny is equals to n naught exponential of psi y by phi t. Again, this is based on junction law. Following the same, we can write the concentration of hole at the surface, which is given by Py is equals to P naught exponential of minus exponent, because the hole concentration near the surface is decreasing based on applied gate voltage. So it is minus exponent. Now what is the total charge density here in this region? So the total charge density can be written as psi y is equals to q times the hole concentration, which is given by P naught exponential of minus psi y by phi t. The electron concentration, which we need to take as negative because the sign of electron is negative, n naught e to the power of psi y by phi t. There is another charges, which is what? Acceptor ions and the donor ions. Again, we are calculating the general formula, so we need to consider both at this stage. So, plus Nd minus Na. So, this is the total charge density per unit area in this region, which includes the electron, holes, acceptor ions and donor ions. Now, can I relate this charge density equation with a voltage? What voltage? This voltage psi y, which I am interested to calculate in, right? So, using Poisson equation, we can relate the charge and the potential, which can be given by delta square psi divided by delta y square is equals to minus of rho y by epsilon s, where epsilon s is the permittivity of silicon. It can be given by relative permittivity into, so this is nothing but 8.854 into 10 to the power of minus 14 farad per centimeter into, for semiconductor or for silicon it is 11.7 approximately. So, this can be written as farad per centimeter. So, we will write the Poisson equation like delta square psi divided by delta y square is equals to minus q times q over epsilon s into p naught e to the power minus psi y by phi t minus n naught e to the power of psi y by phi t plus Nd minus Na. To get the space, I am just cleaning this. So, how can we solve this equation? This can be solved by multiplying 2 times of delta psi by delta y both side and integrate both side by considering a dummy variable y. So, we can do that 2 times d psi by dy into d square psi divided by dy square is equals to minus of q by, or it becomes 2 times of q by epsilon s into p naught e to the power minus psi y over phi t minus n naught e to the power psi y by phi t plus Nd minus Na into d psi by dy, and you integrate both sides. For the integration, you require limit. What will be the limit? Again, you come back to the structure, you see we are actually calculating the potential from this dimension along the body. So, below this point, below a certain point, the body will be considered as a neutral, because the depletion region expansion will stop at certain point. This is similar as p-n junction theory, which says that the depletion region expansion will stop after a certain point, and these regions are known as neutral region. In neutral region, we considered that the electric field and the potential is 0. So, ultimately what will be the limit of potential, the surface potential what we are actually calculating, it is nothing but 0 to psi s, where psi s is the surface potential exactly measured at this point. Now, what is the limit of left hand side? So, left hand side quantity can be written as delta psi by delta y whole square d by dy. So, you see the left hand side shows the electric field, because the differentiation of potential is nothing but electric field. So, you need to put a limit of electric field which is 0 here, and some electric field exists at the surface, right. So, this is d psi by dy. If you do the integration, you will get d psi by dy whole square is equals to minus 2 times q divided by epsilon s into the integration of this bracket is p naught e to the power of minus psi y by phi t into minus of phi t minus n naught e to the power of psi y by phi t into phi t plus Nd minus Na into psi y, and you put the limit 0 to psi s. After putting the limits, you will get, you first of all you take negative sign outside. So, it is 2 into q divided by epsilon s, and put the limit of psi s, you will get phi t p naught e to the power minus psi s by phi t minus 1, As you have taken negative sign outside, it becomes plus phi t n naught e to the power psi s by phi t minus 1 and minus or plus Na minus Nd into psi s. So, this is the equation where left hand quantity delta psi by delta y is nothing but electric field, but this is an electric field square. So, I can rewrite this equation here as delta psi by delta y whole square is equals to 2 into q divided by epsilon s into phi t p naught e to the power of psi s by phi t minus 1 plus n naught phi t e to the power of psi s by phi t minus 1 plus Nd minus Na into psi s. You know all the quantities here. Now, this is similar as the left hand side quantity delta psi by delta y square is some function of psi s. It means if I am interested in what is the electric field, so delta psi by delta y is equals to square root of f psi s plus or minus. Instead of showing plus and minus, can I use some function here which gives me the value of plus and minus based on this function? This is a good signal which is called as signum function, signum of some parameter in the parenthesis, which can be given as a positive or negative based on the values of that parenthesis. So, signum function is defined as plus 1, let us say I am plotting a signum function with x. So, if my x is positive, then the value of signum x is plus 1. If x is negative, then the value of signum x is minus 1, and at x is equals to 0, the value of signum function is 0. So, can I replace this plus and minus sign here by a signum function? But I need to choose what parameter I should keep in this parenthesis. So, I can choose any parameter which will give me the direction of the electric field. For example, I am choosing the dimension or parameter as electric field at surface and minus or towards the bulk. Other parameter what I can choose is the field or the potential at surface minus the potential at bulk. If I know the potential at surface and the potential at bulk, I can decide from which direction the electric field will go, right, or the direction of the electric field. So, if I write this can be written as psi s minus bulk potential is 0. We just claimed that in the neutral region the bulk potential will be 0. So, this is psi s. In general, we take the parenthesis parameter as psi s. So, ultimately this equation can be rewrite as delta psi by delta y is equals to signum of psi s into 2q by epsilon s into phi t p naught e to the power minus psi s by phi t minus 1 plus n naught e to the power psi s by phi t minus 1, okay, here phi t will also come, plus Nd minus Na into psi s. Now, this dimension or this quantity is electric field, but the negative of electric field, correct, and this can be replaced by a charge following a Gauss's law. So, this electric field is will give me a charge Qc dash by epsilon s. So, if I am interested in Qc dash, what is the channel charge, then I can simply write Qc dash is equals to minus of signum psi s into square root of, here I forgot the square root, sorry, this will be square root because following this there will be a square root, right. So, square root of 2 into q by epsilon s into there will be an epsilon here, there will be an epsilon, right, epsilon s into epsilon s into again the same quantity phi t p naught e to the power of minus psi s over phi t minus 1 plus n naught phi t e to the power psi s over phi t minus 1 plus n d minus n a into psi s whole power 1 by 2. If you simplify this, you will get a general expression minus signum of psi s. This will give you 2 into q into epsilon s. Can I do something to calculate P naught out from this structure or from this equation? Let us apply some boundary condition here. So, let me rewrite before phi t P naught e to the power of minus psi s by phi t minus 1 plus n naught phi t e to the power of psi s by phi t minus 1 plus n d minus n a psi s, which is power half. To further simplify this, we will go for a boundary condition. We know that the charge density was given by the whole contribution. It means P naught e to the power minus psi y by phi t minus electron contribution n naught e to the power psi y by phi t plus n d minus n a, right. What will happen in the flat band condition? So, at flat band, condition, we know that the charge across the surface or the charge at the surface is 0 and the potential is also 0. If we keep that, the charge neutrality equation holds good and it will give you P naught e to the power 0 minus n naught e to the power 0 plus n d minus n a is equals to 0. So, we can simply replace n d minus n a n naught minus P naught. I will replace this n d minus n a here, and one more replacement I can do as n naught can be replaced as P naught e to the power of minus 2 phi f over phi t. In previous lecture, we have discussed that part, that n naught can be given as ni exponential of minus phi f by phi t and P naught can be given as ni exponential of phi f by phi t, considering the body or substrate is of p type. So, by using these two equations, we can rewrite n naught in terms of P naught. By feeding all these in the above equation, a closed form equation of Q c dash will become up as minus of signum psi s square root of 2 into q into epsilon s into phi t P naught e to the power of minus psi s by phi t minus 1 plus n naught here can be replaced by P naught, right. So, it is P naught e to the power of minus 2 phi f over phi t into phi t into e to the power of psi s by phi t minus 1 plus again n d minus n a can be replaced by what? N naught minus P naught into psi s. So, it can be written as n naught into psi s. So, P naught e to the power of minus 2 phi f by phi t, this is in terms of n naught into psi s minus here n a can be replaced by minus P naught. So, ultimately this will be P naught into psi s to the power half. If you take in every parameter, if you see everywhere we have P naught, I can take it out, and P naught is nothing but what is exactly equals to Na, which is body doping. So, ultimately minus signum of psi s square root of 2 into q into Na into epsilon s, you will get a closed form equation as phi t e to the power of minus psi s by phi t minus 1 plus phi t e to the power of minus 2 phi f over phi t e to the power of psi s by phi t minus 1 plus p naught you have already taken out psi s e to the power of minus 2 phi f over phi t minus psi s. So, if we see the closed form equation, we are here. We have already put or replaced this n naught by p naught e to the power of minus 2 phi f over phi t, and na and nd is replaced by p naught minus n naught. So, you keep all those quantities and you will ultimately get this equation, where this is a closed form equation which relates the channel charge QC dash with respect to surface potential. Here one quantity, this quantity can be simplified as the square root of 2q into epsilon can be simplified by keeping all those known parameters, like what is q? It is an electron charge 1.6 into 10 to the power of minus 19 coulomb. Epsilon, what we have already discussed, it is permittivity of air and then semiconductor. So, epsilon naught times of this. So, let me summarize. We have discussed a general closed form equation or a unified model which relates the channel charge and surface potential in a two terminal MOS cap. We have seen that this expression holds good for all values of psi s, whether my MOS capacitor is in accumulation, depletion or inversion. So, in next lecture we will see how this relation can be plotted and interpret in basic physical fundamentals, like what will happen when the surface potential is below flat band voltage and above flat band voltage, and how the charge responds. So, we will stop here for today. Until then, take care.